and we have two intermediate stations, C and D, right? Intermediate points C and D. In these uh, two numericals, which are part of our assignment, we have only one intervening station. Now, some of you may be confused because one numerical, what we did, we considered a new datum. In the first one, we did two examples, right? In the first one, we considered a new datum. Why we considered a new datum? Because the ground in between was uniform. Now we know that datum means what? The RL at all points will be same. Okay. The original datum, the mean sea level RL will be 0. If we consider any reference datum, the RL of that datum must remain constant. It has to have a same value. So in the first numerical, we considered a reference datum because the question said that the intervening ground is having a same elevation. Okay, ideal condition. It will never be like that in real world. Like, but in the second one, it is not like that. We have ups and downs. We don't know what are the values in between, and we have the reference datum is our original datum only. Okay, so sorry, reference datum is our original datum only. So in these two numerical also, what we have to do, we have to take the datum as the original datum only. We have a point somewhere, we have an elevation of a point, and we know this height from the datum. So first we will look at the horizon. Okay, this will be our D. We have this formula to find out H and D, right? Then using that formula, we will find out what is D. We are also provided with the distance between A and B. Okay, this is given. So we will be able to find out what is this distance, right? Because we will know this D from the formula, and this H is already given. This is the RL of point A, or elevation of point A from the datum. Then this line, this passes over here, right? So we will find out what is this H, right? And then in the second time, what we will do, we will look from A to the ground point of B. Okay, this is the ground point of B. Here somewhere we will have our C point, say for example, the intervening point. Okay, this one. In the first formula itself, because we also know the distance between A and C, right? After knowing D, we can find out what is C, and say for example, this point is E. The CE we can find out because we know D minus AC. We know this much. This much we got. This is given. This is again given, right? This D came from the formula, and this is given. So we can find out D minus AC. The CE can come, right? Again, using that same formula, this CE we found this D, right? This is A, this is C, this is given, right? So this minus this, we have this value. Now, at this C point, if we look from this location, we will meet horizon here, right? So same thing. So now in the new formula, we can use this can be the new D and this will be the new H in the same formula. So that way we can find out what is CC1, right? Now after knowing these things, what we can do, we have this way, we are here at A point, we are, this is our B point. We can say that let's try to look from the ground point of A to the ground point of B this way. And this was the our original line of sight through the horizon, right? Here we have C1 like this. We know that value, right? Now we will know this value, right? Because we have already been provided with this elevation of B point. We can find this value from the formula. So this minus this, we can find out this, right? Then again, we found this value that will be required later. Now we all know now this value is known. This value is known, right? In the triangle. In the triangle. This is known. This is known. This entire is known. This we have to find out. That we can do. Okay, then we can do by using the principle of similar triangle. Okay, so after getting this value, there is this C1 and C2, right? Initially from the formula we got C1 and C this much. Let me draw once more. Like this. Here we have A, here we have B. Right, this was the initial line of sight through the horizon. And now we are looking here. Right? This was our C point. C to C1 we got from the formula, and from C1 to C2 we will get from the principles of similar triangle. Then we will add them up. Okay, small c, C1 plus C1, C2. We will add them up. This is going to be what? This is going to be the elevation at C point. Okay, or this is the RL of C point, right? Now, when we know the RL of the C point, then we will compare with the given RL of the ground point. Okay. This is elevation of C2 point actually. So RL of C2 point. Okay, C2 point is what? C2 point is the line of sight. Okay, so then we will compare this RL of the line of sight with the RL of the ground level. Now, if we see that the RL of the ground level is above this, then the line of sight is not crossing through this point. But if the RL of the ground is below this point, then the line of sight is crossing this point. As simple as that. Now, if the RL of the ground is above, if this is the case, then what we have to do, we have to provide a signal over here, and then we have to look, right? And then we will again do another set of similar triangle calculations to find out what is the required height of the signal. Okay, so that way you try once more. Okay, is it clear? If not clear, please let me know. Okay, after this we will go for this one. So here we have few theoretical things, very simple selection of triangle. Fixing our equipments over there. It may be a theodolite, it may be a total station, it may be an electronic distance measuring equipment like that. Okay, so those stations are to be, workable. You have to be able to reach there, you have to be able to work over there properly, things like that. So one important condition that it must form well-conditioned triangles. Now I hope you remember the definition of well-conditioned triangle. It is necessary so that we have greater accuracy in our measurements. So we will try to have well-conditioned triangles in the network of triangle. Fine. So please see these points. Okay, will discuss about the correction to tape measurements. Now we use tape or chain to measure something. Then there may be some errors. Okay, and when there are errors, we will have to provide correction to those errors. Right. So what can be these corrections? Correction for absolute length. What it means that the chain is written as 30 meter, but it is not 30 meter in actual length due to some errors, due to some defects in the chain or the tape. It is, say for example, 29 meter only. So what we will do, we will end up measuring 29 meter, but we will note down 30 meter. So there is an error of 1 meter. Fine. So that is one case. Pull or tension, what can happen if we are pulling it very hard, they're more than the standard pull. Okay, then what may happen, maybe it is stretched a bit and now it is not 30 meter, it is 31 meter, say for example. So now we are measuring 31 meter and we are writing down 30 meter because it is written as 30 meter in the chain, right? Like that. There can be corrections for temperature because there will be a temperature at which the tape or the chain was standardized. Okay, say for example, it was prepared when it was first measured or calibrated, it was done around 30 degree. Now we are working around 40 degree in an environment where the temperature is 40 degrees Celsius. So there may be elongation in the tape or chain, and then again it is no more 30 meter. It is, say for example, 30.5 meter. Like that, there can be errors, and there we will require uh, corrections to it. Now, one important thing to remember that uh, except this absolute length, it will depend upon it is longer or shorter. We will see all these correction, pull, temperature, sag, slope, these all are going to be the sag correction is negative always, slope is negative always, correction for alignment negative always, reduction to sea level is always negative because you are operating on above the sea level almost all the time. And the pull and temperature, if the pull is higher, correction is positive. If temperature is higher, correction is positive. Let's just see these things. So it's like this. Say this is a 30 meter. It is written as 30 meter, designated as 30 meter. But if we apply a pull greater than it can sustain, then what will happen? This is now elongated to some extent. Say for example, 30.5 meter. Now in the field, if we operate like that, we will end up measuring 30.5 meter, but we will write 30 meter only, right? We will note down 30 meter, but actually this is 30.5 meter. So what is the error? Error is 0.5 meter. Okay, is positive. The error is negative. The error is negative. The correction is positive, negative of negative, it is going to be positive. So when we will add 0.5 meter to this original designated length, then only we will get what is the actually measured value. So two things to remember in case of pull and temperature. If these values are higher than the standard value at which the tape was standardized or it was calibrated, then the correction is going to be positive. For all other cases like sag, alignment, the correction is going to be negative. So this is what we were supposed to measure. If our chain is like this, obviously we will end up noting down some value which is greater than this value, right? Say for example, this length is 20 meter between A point and B point. If we do not hold our chain or tape properly, then definitely this is going to be greater, right? Say 22 meter, right? So the correction here will be minus. Negative, right? Then only we will get 20 meter. So this is always negative, because if there is some kind of sag like this, the value is always going to be greater than the actual value, right? If there is misalignment, looking from the top, say for example, this is A point, this is B point, we should measure it this way. This is, now we are looking from the top, but we measure it this way, right? Say for example, then this value is obviously going to be higher than the value between A and B. So the correction is always going to be negative to get this value. Say this is 20 meter, again say for example this is going to be 25 meter if you measure it in a curved way. So that's it, as simple as that. So there are some formulas to correct this absolute length. Let's see what happens in absolute length. This is 30 meter, written as 30 meter, but the chain is actually shorter. Say for example, so it is 29 meter, right? So we will measure, this is 29 meter. We have measured 29 meter, but we have written 30 meter. We have an error here. We need correction. What we have to do, we have to reduce this value. We have written it 30 meter, but in reality it is not 30 meter, it is 29 meter only, right? So in 1 meter we can do, in 1 meter, in one chain length we can do, right? But if it is a greater length, if we have measured, say for example 200 meter with that same chain, right, and we have some errors over there, okay, then we have to use these calculations, very simple calculations, and what is the error in 1 meter, and then what is the error in 200 meter, right? What is the error in 1 meter? How we will get error in 30 meter is how much? Error in 30 meter, we have 1 meter of error, right? That way we will get. So this is the correction here. L is what? L is the measured length. C is the correction part tape length, and L is the designated length. So it's like this. We have written 30 meter. In 30 meter, we have 1 meters of error. So therefore, in 1 meter, we have 1 by 30 meters of error. Now, whatever length we measure, say for example, we measured 250 meter. So very simple, 250 multiplied by 1 divided by 30, right? So this is the error per tape length. This is the designated length of the tape, and this is the length that we have measured. This will give us the correction. So we are writing CA, that is the correction. So we are writing correction and C and small l. So this C is the correction per tape length. Okay. This capital L is the total measured length and small l is the designated length of the tape. This will give us the correction required in the entire calculation. Then correction for temperature. This is the same formula that we use for thermal expansion, right? So this is the same formula, alpha Tm minus T naught. Tm is the temperature where we are doing our measurement. T naught is the standard temperature. When the tape or chain was first calibrated or measured, okay, this is a 30-meter chain or 20-meter chain. At that point of time, it was done in which temperature? That is a standardization temperature, right? So this is the value and capital L is the measured length. So this is the same formula for thermal expansion. So this formula, if Tm, the measured temperature is greater than the original standard temperature, this value will be positive, correction will be additive. If this measured temperature, where we are doing the measurement, at which temperature we are doing the measurement, if this temperature is lower original temperature, then this value is going to be negative, right? So this formula is directly giving us if the correction is positive or negative. Okay, I have given two few lines, please see those. Correction to pull. Now this formula, you know this formula from strength of materials, right? This is the linear axial expansion or contraction, push or pull, right? In our case, if we are giving pull that is greater than the standard pull. So P is the pull that we are giving and P naught is the standard pull, right? So if our pull is greater than the standard pull, then obviously there will be extension and this value will come out to be positive. Correction is going to be positive. And if the our giving pull is lower than the actual pull, then actually there will be some sag. There may be some sag, and this correction will come out to be negative, and that will be added to this final value. Okay. So this is correction for sag. This A point and B point, between this point we had to do our measurement. This should have been a straight line, but due to negligence, it is not a straight line and we have some sag here like that. And from that, we will have some errors. Now, if there is sag, always the correction is going to be a negative because this value is always going to be higher, right? This value is always going to be higher, so the correction is always going to be negative to get the original value. So this is our formula. What is CS is the correction for sag, small l is the total length of the tape. This is going to give us the correction per tape length. If we L small l tape length, W is the weight of the tape, N is the number of equal spans, and P is the pull applied. Okay, so it's like this. If we are doing our calculations like this, right? This is, we're carrying out our survey like this. So we have sag in every time. We have some sag in every time, right? So that way. How many numbers of times we are carrying out the calculation? That is our N, number of equal spans. Okay. Then correction due to slope or vertical alignment. Okay, so this is A point, this is B1 point. We had to do this way, but we didn't do this way. We went to some other point, right? So therefore, we have this error over here. So very simple things. The formula, few of the formulas we have to remember. Few formulas we already know, like the temperature correction we already know, and pull, the strength of materials formula that we already know, the correction for absolute length that can be done by unitary method, and two other formulas that we have to see and remember. So vertical alignment, we have, it's simple to these sag or misalignment, same thing, same concept, because we had to go from A point to B point. We didn't go to that way. Okay, we had some slope, we did it in a different direction. Okay, we misaligned our measurement, so then we will have this error. So this will become a little bit clear when we see this and when we do one or two numericals of this. Okay, correction for horizontal alignment, these two are exactly similar, just the direction. Okay, in the horizontal plane or in the vertical plane we are making our error. Other thing are exactly same, their formulas are also exactly same. Okay, so because this is horizontal alignment, therefore we are writing D because it is in the horizontal plane, okay, in the ground itself in a different direction. The earlier was in the vertical plane, that means you were going up or down, okay, then what you were supposed to do. So therefore that error, but the formula is exactly same. This D is the difference from the original point, that's it. Then deformation of the tape in the horizontal plane. In the horizontal plane itself, if we are not measuring it properly, same kind of thing in the when we say misalignment, say for horizontal plane, we are on the ground surface. This is A point, this is B point. We had to come from A to B, but we went somewhere there, not going exactly to B. That is one kind of error. But in this error, there can be one more error. We went to some point and came back to B point. We had to go from A to B directly, but what we did, we made error. We went this way. Okay, so that is another error. Okay, so these are the different types of error. When we see the numericals, things will be a little clear. For now, you do the problem of triangulation, the intervisibility of stations, and see a little bit of these errors. Next, we will discuss again few of the numericals. When we discuss the numericals, I hope things will be clear. And here, what is invert tape? This is important information here. Please read this. Invert tape is accurate. It gives an accurate measurement. Why? Because the coefficient of thermal expansion of invert alloy is very low. So therefore, what we have, the errors are much less than other type of tape. Okay. So this question is often asked, that what is invert tape and what alloys they are consisting of. So 36% is nickel and 64% is steel.